In this video, we're going to introduce the Sturm Liouville theory. This is a bit more of an abstract way of looking at ODEs in general. So I hope that with the background that we have just reviewed on linear algebra, we are able to look at this extension and this way of looking at ODEs with enough clarity. So the Sturm Liouville theory is built on the Sturm Liouville problem. This is a second order ODE with non-constant coefficients in which we have pxy prime, all of it derived, plus qxy plus lambda wx times y, all of it equal to 0. And we want to solve it between a and b. And we have some boundary conditions. This is different than what we have seen up to now because we don't have only initial conditions, we really have conditions both at the beginning and at the end of the interval. And they're possibly mixed in the sense that we have some information on y and some information on y prime. So we know that the sum of y times a constant plus y prime plus a constant is equal to 0, and the constant depending if we're looking at I, a, or b. So at the beginning or at the end of the interval we are interested in. And we have some restrictions on what sort of conditions we can have. So we know that looking at the boundary conditions, a and b, alpha and beta are not both 0, and gamma and delta are not both 0. So these equations actually do make sense. And px is always positive and wx is always positive in the interval that we're looking at, so between a and b. We want to solve for lambda and y at the same time. So if you're looking at the equation again, px, qx, wx are things we know about. Alpha, beta, gamma, and delta are also given. What we don't know is lambda and y. So it's a bit of a broader question that we have than what we have usually been looking at. Let's look at an example to make this a little bit more concrete. We're looking at the problem y second plus lambda y is equal to 0. We're looking at it between 0 and capital L, and we're imposing 0 boundary conditions on both sides of the interval. From the characteristic equations, we know that, well, we either have y second equals to 0, that gives us something that cannot fit our boundary value problem, or we have a sum of sine and cosine of square root of lambda x. And now we want to look at the constants in front of the sine and the cosine, and we want to use the boundary conditions in order to fix them. So we know that at 0 we have trivial boundary conditions, and sine of 0 is 0, so the only element we have at 0 is a. And we can look at capital L, and here we have a cos square root of L capital L plus b sine square root of lambda capital L. Then we impose the boundary conditions, and we find that a is equal to 0 because of our boundary condition at 0, and b times sine of square root of lambda times capital L is also equal to 0. So we either have that b is equal to 0 or that sine square root of lambda capital L is equal to 0. But b equal to 0 will give us a completely trivial solution all the time, and that wouldn't be very interesting. So we look at a lambda that satisfies our second equation. So sine of square root of lambda times capital L is given, needs to be equal to 0. So this allows us to solve for lambda, because if sine of square root of lambda times L is equal to 0, then we know that square root of lambda times L is equal to some integer multiplication of pi. We can go negative, but then we have to square everything anyway, so it's not very interesting. So we have that lambda is equal to n squared times pi squared divided by capital L squared, where n can be any value in the natural numbers. We say that lambda is an eigenvector associated with the eigenfunction sine of n pi divided by L times x. And both of this eigenvalue, lambda is an eigenvalue associated with the eigenfunction y, both of them are valid for any integer, positive integer n. So if P is a Sturm Liouville problem, then a solution lambda y is called an eigenpair. In the same way as we were looking at for matrices, we can talk about eigenvalues, we can talk about eigenpairs, and y is a function now instead of a vector, so we call it an eigenfunction. We have a theorem that if your ODE is in the form of Sturm Liouville, so if you're looking at a Sturm Liouville problem, you have countably many real distinct eigenvalues. What does that mean? Countably means that you can count them. So they are in one-to-one correspondence with the natural numbers. You can order them as lambda 1, lambda 2, lambda 3. They're real. So you don't have to look at complex values, and they're distinct. So each one is different. That means we can count the eigenvalue in increasing order. So we can look at the smallest eigenvalue, call it lambda 1, and then we have lambda 2, lambda 3, and so forth. Technically, in order to count them, they could be like, you could have lambda 1 being, how to say? You can have things that go to infinity on both directions, but with some restrictions, we actually know that they're all positive. And they tend to infinity for n tending to infinity. In this video, we're going to look at self-adjoint operators. And I'm going to claim that self-adjoint operators are the symmetric matrices of functions. So symmetric matrices have a lot of cool properties that we can use when we're looking at a finite vector space. So we have a space in which we can look at finite vectors such as Rn, and with symmetric matrices we have a lot of properties that allow us to play with these vectors in an easy way. And self-adjoint operators that we can build from Sturm Liouville problems, and we're going to see in this video how we build them, they correspond in a lot of ways to symmetric matrices. So the first thing that might be very minor, but they're going to be very important when we're going to be building it up, is what is the correspondence of inner products when you're looking at Sturm Liouville. So we have seen inner products when we were looking at vectors. We have introduced it again sooner this week, in which we take two vectors and we multiply them by each other by just summing the product of each element of the vector with the next. Can we extend this concept of inner product for functions? Yes, in a very general sense, yes. Looking at specifically Sturm Liouville problems, we're going to define the inner product depending on the Sturm Liouville problem that we're looking at. And we're going to define it as the integral from a to b of f times g times w dx. So w comes from our Sturm Liouville problem. The bounds a and b comes from our Sturm Liouville problem. Well, f and g in this case are two functions. Two functions that are still satisfying the boundary conditions of the Sturm Liouville problem, but don't need to satisfy anything else. So W, A, and B depend on the problem that we're looking at. So we're looking at the Sturm Liouville problem, and we want to build a differential operator. So we have Px y prime all prime plus Qxy equals minus lambda Wxy plus some boundary conditions. Now I want to build an operator in the sense of the Laplace transform. So I want to build something that works as a function for functions. Something that takes a function and spits out a function. So I define the operator H that takes my Pxy prime all prime plus Qxy plus the boundary conditions and spits out something that again satisfy the boundary conditions. So it takes in y and spits out my left-hand side. And I want to build a correspondence between this completely random operator that I just built and the symmetric matrices. So first of all, I want to say that if in some senses the inner product that I have just defined before works in the same way as the inner product that I have looked at before when I'm looking at symmetric matrices. What do I mean? When I was looking at symmetric matrices, I said that the inner product of x times ay is equal to the inner product of y times ax. Now for h being an operator, I want to prove that the inner product with f times hg is equal to g times hf, where f and g both satisfy the boundary condition of my Sturm Liouville problem. Let's look at our example and test it out. So I want hy being equal to minus y second. We want to keep the minus with us because we don't want to put the minus with the eigenvalue. So if we're looking at y second equals minus lambda y, we have the minus in front of the eigenvalue, and that is not very nice. Instead, we take the minus with the y second. So we have h of y being minus y second. We have boundary values on both sides. In our Sturm Liouville problem, we have w being constantly equal to 1, so we don't really have to take care of it. And we have introduced the inner product f comma g equals to the integral between 0 and L of f times g dx. And we want to check that the inner product of f times hg is equal to the inner product of g times hf. And we can do this by partial integrate. The division, when we're looking at integrals, the idea of splitting derivatives between the two functions that they're multiplying with. And it turns out that yes, it does indeed work for this case. I'm going to claim that in general, if we're building an operator, as I told you before, up to a sign that I might have forgotten, then indeed it corresponds to the symmetric matrix in the sense that this equation holds. Inner product of f times hg is equal to the inner product of g times hf. And if an operator satisfies this switch of functions with respect to the inner product, where the functions do satisfy the boundary conditions, and the inner product is the one that comes with the operator in a certain sense, then we define h as being self-adjoint. And we are going to be built a lot on the relationship that self-adjoint operators have with symmetric matrices. The most obvious place in which this relationship between the two can be seen is when we're looking at the spectrum theorem for self-adjoint operators. So we say that if lambda I, yi, and lambda j, yj are two eigenpairs of our associated to our operator h, remember that when you associate eigenvalues and eigenfunctions to our operator h, you have this wx popping up. We don't have it in our example because wx is equal to 1, but you have to remember about it. So we're looking at this eigenpairs associated with our self-adjoint operator. We require the two eigenvalues to be different. Then, if h is self-adjoint, the inner product between yi and yj is equal to 0. In some senses, we're extending what we know about symmetric matrices to this much more abstract statement about self-adjoint operators. So in this case, yi and yj are orthogonal with respect to the product, defined by our Sturm Liouville problem to be the integral between a and b of each element times w.